Yeah, one thing that where GPUs were mentioned regarding deep learning is when guys at Stanford reproduced results that were obtained by Google on their gigantic CPU infrastructure using just a couple of GPUs, because with 12 GPUs they were able to reproduce the results that Google obtained on 2,000 CPUs. And there was a big announcement saying that GPUs are very good at deep learning for training your deep neural nets, and that's one kind of thing that has been mentioned about GPUs and deep learning. So I'm not going to teach you how deep learning works or how machine learning works, but basically we have two important phases. One is the training, the other one is the classification. At the moment, you've probably heard a lot about using GPUs for training, and I have a couple of examples coming in the next few slides. GPUs are also useful for classification if you have a data center and want to do a lot of classification. But also in our portfolio, another piece of our hardware is useful for classification. I'm going to show you an example in a few minutes. It's the Tegra embedded processor that could be used for classification. So let's start with a bit of training. In particular, these days, GPUs are very are used extensively in one typical problem where you want to do classification of images, and you especially want to use a special type of deep neural nets that we call convolution neural nets. It is a type of neural net that was invented at the end of the last century, so 15 years ago, even if it sounds like a long time ago. And the idea is that you have a lot of 2D convolutions, or maybe 3D convolutions, but if you want to work on 2D images, you have a lot of 2D image convolutions. And these 2D image convolutions are very efficient on the GPU. One first sign of using GPUs for that kind of task on these convolution neural nets was shown in 2011 by Dan Cherizan, who used GPUs to train such a deep neural nets, convolution neural nets, to recognize traffic signs, German traffic signs. They're not so different from French traffic signs, but German traffic signs. And for us, the biggest improvement in using GPUs for training in deep neural nets and convolution neural nets happened in 2012, where Alex Krzyzewski, I'm sorry for his name, invented what is called AlexNet, which is a well-known network in the deep learning community to solve or to compete for the ImageNet challenge. Well, the goal is to take images and classify the images. So if you have a dog in your image, the net is going to tell you that you have a dog in the image. At least this is what your algorithm is going to do. And what was really interesting in that work is that it was able to reduce the error rate of its classification of its nets. And starting from that, each year we've seen an increasing amount of teams competing for this ImageNet challenge, doing classification of images using GPUs. As you see on that graph, in 2012, there were 15% of the teams using GPUs in that challenge, and in 2014, 95% of the teams are using GPUs to compete in that challenge. In other words, if you want to compete in that challenge, you better use GPUs. The truth, to be totally honest, is that the winner is not using GPUs in that case in 2014, but you either need a GPU or a gigantic infrastructure. And 2014, you had these results, and very recently, at the beginning of this year, we've got new results like Baidu announced that they reduced the error rate to about 6%. They were using GPUs. And a few days ago, Microsoft came and said, yeah, we were able to so past the human level of performance with our deep neural nets, and we do use GPUs. I think something like half an hour after Microsoft announced the results, Google say, yeah, we do better. And I did not put that one on the slide because maybe, I don't know, in the next 5 minutes, someone else is going to announce something even better. So we never know, but these days things are moving very, very quickly, and most of these results use GPUs to get good performance. And this is on classification of images, but this is not the only thing you can do with GPUs to train networks. You don't need to train convolution neural nets that are used to classify images. We have examples of other kinds of networks that were trained using GPUs. For example, at the very end of last year, Baidu announced a system to do speech recognition, and they trained their system with GPUs, and this neural net is using recurrent networks, recurrent layers in the network, and that's another kind of layer that could be interesting. Other examples are LSTM, long short-term memory layers that could be interesting, and for all those different kinds of networks, you can use GPUs, and GPUs are quite popular these days for that kind of challenges. Just a few days, like weeks ago, at the CES conference, we've actually showed an example of a deep neural net, convolution neural net, used. So this convolution neural net was trained on GPUs, and we were using this net live on a car to do classification of other vehicles on the road. So this is an example of this is a street next to the NVIDIA office in California, and the neural net is able to classify the different kinds of vehicle in the street. So that's a car, that's a bike, that's another car, a cool car. Does it say if the car is cool or not? No. That's a bus, and that kind of things. And this, the classification, real-time classification, is running on a Tegra processor. It's an embedded processor in one of our new modules that we announced at CES, which is called Drive PX, which contains two embedded Tegra processors, Tegra TX1. And we are able to do classification real-time using this deep neural net. And we expect that it's the kind of technology that is going to become very, very important in the car industry very soon. And we're very excited about that. So I've talked a bit about the deep neural nets and that kind of things, and GPUs for deep neural nets. Just to give you a few words about the products we develop in our architecture. So I don't know how familiar you are with the GPU architectures, but at the moment we're in between these two architectures. In the market we have the Kepler architecture that is available and the Maxwell architecture. Kepler is available in professional devices like the Tesla K20, K40, and K80. In the different papers I cited, this is the GPU that these guys use to train their networks. And our other architecture, Maxwell, is used in the gaming industry like GeForce GTX 970, 980, and that kind of GeForces. The next architecture that we are planning to release in 2016 is called Pascal, sorry. And there are two really cool features that we believe are going to be very interesting for machine learning and deep neural nets in particular. One is very high connection between different GPUs. So if you're familiar with deep learning on GPUs, you know that scaling to multiple GPUs is quite a difficult thing to do. And especially because GPUs are very good, very efficient, very compute powerful. I don't know if we can say that. And the communication between two GPUs is much more difficult because the bandwidth between the two GPUs is much lower than the bandwidth inside the GPU. And NVLink is our proprietary link connection that we developed to have a faster connection between two GPUs. So just to give you a sense of what we are able to achieve, today GPUs are connected through the PCI Express bus that runs at about 16 gigabytes per second. And tomorrow with NVLink, it's going to be connected at about 80 gigabytes per second. So if you're not a hardware architect, you may not know that 80 gigabytes is more or less the speed of your DRAM on the CPU. So it's going to be as fast as going to the DRAM on your CPU when you communicate between two GPUs. And we believe that it's going to be a major thing for deep learning on multiple GPUs. The other very cool thing that we're going to add to the Pascal architecture is what we call stacked memory. Basically, all the hardware vendors are going this way. It's going to be it's a different technology of GPU memory, and the bandwidth is just going to grow crazily high because we are going to be at about 1 terabyte of bandwidth. Today we're about 300 gigabytes on the strongest GPUs, so it's going to be a triple in bandwidth, and we'll also have very large capacity. So if I put things in perspective for deep neural net and convolution neural nets and that kind of things, you're really happy to have high bandwidth for fully connected layers, because these layers are clearly limited by the memory bandwidth. You also possibly happy to have high bandwidth for convolution layers, because the convolution, depending on how you implement it, is either limited by the compute power or the memory bandwidth. And very recently, new results have been announced on using FFT-style convolutions. These are going to be very sensitive to the bandwidth, so high bandwidth is going to be something really useful for you. Just a word, maybe you know that. It's more kind of marketing business slide, but the idea is that we have different kind of GPUs, and we recommend to use the Tesla GPUs for our servers and use the GeForce, for example, GeForce Titan to do the developments. And especially what we often observe at our partners doing deep learning is that they use GeForces to develop and they deploy on Tesla GPUs in their data centers. Just for you to know, and if you have questions, I'd be happy to answer these questions. So hardware is one thing. We're also working on a more software-oriented layer for deep neural nets, and NVIDIA is heavily investing in this, and we have basically developed a library that implements some of the building blocks that are needed for deep neural nets. This is called QDNN, and you have implementations for convolution layers, forward and backward propagations. You have pooling, activation functions, and softmax. It is in RC2, I think, Tuesdays, and it's going to be released final very soon. And I recommend you to go there and double check. But if you don't want to do that library directly by yourself, it is actually already integrated in 3 main frameworks: Caffe, Torch, and Theano. All the 3 frameworks are using this library as a building block to achieve good performance on the GPU. So if you're doing research in deep learning, you're writing in Theano or Torch, and you want to get good performance on the GPU, yeah, it's already supported by these frameworks, and I really recommend you to try. We are really working tightly with these guys to make sure they use our library in the proper way and to make them happy. I actually have an email in my box. I got an email in my box 5 minutes ago from one of the developers, so. just very quickly to summarize our support of the different libraries. All these libraries, as I told you, they integrate, or the three libraries, Scaffi, Torch, and Theano, these three libraries integrate QDNN, and these guys are working on multi-GPU support, and we are really helping them improve the performance. Some of them are able to also run on Tegra embedded processors. We hope they're going to be able to also run on it soon, but I have enough materials regarding that. Finally, just a word about, because I mentioned that, TX1, our Tegra processor, it's a new embedded architecture. It's composed by a GPU made of 256 maxwell cores. This is, I would say, about half the performance of a GTX 750, which is a desktop GPU. The GPU on the Tegra TX1 is able to achieve about 1 teraflop of 16-bit computation, and quite a high number if you've been in that industry for quite long enough. You know, these are quite high. And it is an embedded processor with ARM CPU with 4 A57 ARM cores. These are big cores, and we also have little cores for power consumption. That's the typical design in the ARM world. So if you have questions, I'll be happy to answer your questions. But just before I finish, a few words. First of all, I came with my colleague, Guillaume Barra. If you have questions, he's there, and you all can also ask him a lot of interesting questions. Finally, almost last word, next March, we have a conference in California called GTC. There is usually quite a good stuff there, and this year we'll have keynotes by some of the best guys in deep learning, and I'm pretty sure it's going to be very interesting. So if you want to attend, it might be a bit too late, but you can try. And next year, anyways, put that date on your schedule. I think it's still time to go to this year, but I'm not entirely sure. And finally, also because Heuritech say the same, but also INRIA, and especially if you are a community manager and you're interested in deep learning and that kind of things, it's probably a good idea to come to NVIDIA. That's a funny company, so I recommend you to apply. Okay, thank you.
You have something similar to support a Java interface. You mentioned Café and all this Torch. So there was something called JCUDA, but I don't know how current it is.
So, well, first of all, these frameworks are frameworks in general for deep learning, so they're not just interfaces to different languages. I don't think we have a very big Java support. It's basically CUDA is something that you can interface with C. So from Java you can call GNI, but we don't have an automatic way to translate from Java to CUDA. That being said, I've heard about some work done on this, but I don't know if it's all public, so I prefer not to answer it. I don't want to leak anything by mistake. Yeah?
Yeah, a question about the power level, that's the power use of these chips, and especially the last one, the one that's going to be coming up in 2016. I was wondering if you could give us an idea on how those power levels were increasing, not increasing, staying steady with additional type of capabilities.
So let me clarify. What do you call the power? Is it the watts or?
Yeah, precisely the watts. when it's basically running some linear algebra type of, so the most intensive type of computations.
So first of all, the GPUs are going to be standard boards like running at 300 watts. So today our GPUs are either running at 235, and we have some at 300. So take the K40, it's running at 235, and the K80 is running at 300. It's going to be the same thing, but you're going to get much more flops for that price. I don't remember the numbers exactly, but I think we expect something about, take it with a grain of salt, it's not 100% sure, but we expect something like about 4 teraflops, double precision in Pascal or something like that. I don't remember exactly the numbers, but that's the idea.
And so that includes also the link to the GPU, because you were essentially specifying that the new chips were essentially getting bigger on the bandwidth from the memory all the way to the GPU itself. So we're counting also that is the 50 watts on top of what we have right now would also be part of that budget?
Yeah, the budget I'm giving you now, it's everything included. It's you take your board, you plug it, and you need an input to the board that amount of power.
And the other idea that people are using Tegra's, and I think that's basically part of the video for the car. They're basically using Tegra's, at least embedded type of the GPUs, which I guess are Tegra's. And those are much more low power. They're like in the 10 watts type of.
Yeah, the Tegra TX1 is about 10 watts to operate. So it depends on the frequency set and that kind of things, the CPU workload, but let's say 10 watts is a decent estimation.
Okay. Thanks.
You're welcome. Yes?
You said at one point that people in practice are developing on GeForces and deploying on Teslas. Could you expand on the motivations behind this?
Well, basically, open Amazon and check the price. The GeForce is much less expensive than Tesla, but, and this is the big but, you're paying for something if you pay higher price. So on Tesla, we have support for ECC memory, so error correcting codes work on Tesla. They don't work on GeForces, and you also have a better support. The GPUs that are selected to run on Tesla, they go through more tests and all that kind of thing. So basically, if I want to give you a quick picture, it's a GeForce, it's great. If you put it in your workstation, you're a gamer. If one pixel goes wrong from time to time, it doesn't matter. So you're basically doing the work, the development. And the Tesla is a GPU that is really calibrated to run in your data center. Nothing goes wrong, or this is what you expect. And you have ways to control when an error happens and that kind of thing. So this is really the GPU that you want to be running 24 hours, 7 days a week. So this is really the idea. GeForce is good enough if you do development, and Teslas are what you need if you want to run data center, a server, or a simple computer. Obviously, nothing prevents you from using a Tesla for development, but the other way is not correct.
Okay.
You can't use a GeForce in your server. Does it answer the question?
Yeah, thanks.
Any other question? Yes.
One last.
You have shown the roadmap for the progression of your GPUs in terms of increasing computation capabilities. But what about instruction already implemented in hardware? You talk also about the software platform with some already implemented functions. But what are the basic element instruction already embedded in the actual GPUs, and what is the roadmap for that?
So basically, you know that, okay, when you program our GPUs, you have 3 levels of abstractions. One is CUDA, or OpenCL if you prefer OpenCL, but CUDA. The other one is PTX, which is a virtual assembly. And the last one is SAS, which is the binary assembly. Between one generation and the other, PTX remains valid. So if you have a PTX code, you can run on any generation of GPUs. And the last level, assembly, which is the level you never program in, or almost never, it's really tied to an architecture. So the binary that is working on Maxwell is not going to be the same as the binary working on Pascal, or at least you can assume that. So we're changing binaries from generation to generation, but if you program at the normal level, it doesn't impact you. So in deep neural nets, for example, you have an example called MaxDNN, which is an implementation of a convolutional neural nets that is written directly in assembly for Maxwell. It's not going to work on Pascal, and it doesn't work on Kepler. But this is just a specific example of someone writing in assembly. For all the other people, we have a support over time. Does it answer the question?
Not exactly that. It's just like, do you plan to have some kind of instruction that makes the computation of deep learning, or either it is convolutional neural networks or some other kind, going faster without putting in assembly layer? But you know, it will be making the process going faster because it's already implemented in hardware than if it's totally software.
So yeah, the improvement we expect is going to be kind of software, what you call software, because the compute power of the chip is going to be higher on next generation. Now, is the chip going to have new instructions or that kind of things? Well, you have to wait for the GPU to be released to answer that question. But from a software point of view, the software is going to improve.
Right.
Yeah, go ahead.
One last, yes.
Thanks. On this figure in particular, we're looking at SGMM, which must be some type of...
This is a single precision matrix multiplier.
Exactly. Per watts, and that's normalized. Right now we're at Maxwell at about 12. And you're saying that we should be going to Pascal at 20. So that's an 80% growth.
Yeah.
But you talked about going from 250 to about 300.
I mean, yeah, it still makes sense. I mean, you still have the same power envelope, but because you have much higher perf per watt, your perf is just higher. Do you get the point?
Well, I'll do it offline.
Okay, yeah.
Thanks.
Thank you.